possible to generalize expectation and variance to a continuous random variable using this concept that we've defined of the PDF. So for example, the expectation of a discrete random variable was defined as this summation. You weight all of the outcomes by their probabilities. So this can be generalized to the idea that it would be x integrated with this. And as always, we will call this mu. Now we're going to make somewhat of an assumption. We're going to assume this integral exists. We aren't going to get into any of the mathematical details about what properties that function has to satisfy in order to make this integration exist. We will just assume that it does. Now, another property that we had before was if you had to integrate, find the expectation of a function of a random variable, then we are very naturally going to treat this in the same way that we did earlier. It would just be the following integration. So as an example, we had talked about things in the past as follows. So we would say if we wanted to calculate the expectation of a random variable squared, in this notation, it would be x squared f of x dx. Now I'm hoping that you can see the unfortunate idea here is that you will very likely need integration by parts to pull off a lot of these antiderivatives and these integrations. But that's a fact of life with these definitions. One important example that we had talked about before was this linear function of a random variable. So according to the definition we've got here, we would have something like this. Assuming that all of these integrations exist, we'll be able to write things as follows. We can use linearity property of the integral. And again, we can take out constants from integrals because we are assuming that number one, we have a density, and number two, that its expectation exists. So when you split things up in this way, I'm hoping that you can see that this is just by the definition of a density function. That integral has to be 1. And this is the definition of the expectation. So exactly like we had before, this would give us a mu plus b. We also talked about variance. We can define variance in a similar way. We can define the variance of a random variable that's continuous as the expectation of x minus its expected value. But you can also define it in this form with the computational form. We are going to do the same thing here. And similarly, if we ever wanted to figure out the variance of some function of a random variable, we are going to extend this definition like we did before. Whatever letter goes here has to go there and has to go there. So that means this would be the expectation of g of x squared on the inside, subtract the expectation of g of x square on the outside. And just to show you how these properties work, I'm going to show that example about the property that we did earlier. If we wanted to talk about the variance of a linear function of a random variable, according to this definition above, we would have the expectation of ax plus b all squared, subtract the expectation of ax plus b squared on the outside. Now, we have just done this result above, and we know that this is going to be a mu plus b all squared. This particular expression, we could plug in to our integral definition, and we would see that we would get ax plus b squared integrated with the density. As always, we can perform algebra. we get a squared x squared plus 2abx plus b squared f of x dx minus a mu plus b all squared. So as before, we can just go through a bit of tedious algebra, assuming that all of the integrals we need exist, and in particular this integral with an x squared f of x dx. We will end up in a very familiar place very soon. So expanding out that first integral into its constituent parts, we can see that once again, this integral is 1 by the definition of a density function. This is mu. So we'll have a squared times the integral of x all squared dx plus 2ab mu plus b squared. And if we were to expand this portion out, just using FOIL as normal, we would find that some cancellation happens. And we would be left with the variance of our linear function of our random variable would be a squared into this integral minus a squared into mu squared. If we factor out an a squared, we recognize this first integral as simply e of x squared, whereas this second term would be e of x all squared. And so just like we found before, the variance does not care about shifts. The b does not factor into this final result. It only cares about the stretches. So from the phone call example, we could use these definitions to figure out mu and sigma. So the expectation in the phone call example would just follow these definitions. We would get an integral from 0 to infinity x times a quarter e to the minus x over 4 dx, which technically we should write as an improper integral. So limit t to infinity, integral 0 to t, 1/4 x e to the minus x over 4 dx. If you were to use integration by parts, which I'm going to make you do, you would end up getting that the expectation is 4. Now, similarly, if you were to go ahead and calculate the variance, you'd need to calculate this stuff. Well, some of it you've already done. You've already done that this is going to be a 4 squared. This integral would be 0 to infinity, 1/4 x squared e to the minus x over 4. And just like I said above, I'm going to make you do all of that on your own, and you can take a look at that result, and at the end of the day, the variance for that random variable should be 16. So now we've got all of the general tools that we need for continuous random variables. They follow very nicely from those defined in the discrete case, and it all hinges on the definition of a density function. Once we've got the density function in place, everything else